Well, first of all, thanks for having me here today. I'm Fabrizio Frasca, and I'm a research scientist at Twitter, but I'm also a PhD student actually at Imperial College London. Today, we're going to talk about subgraphs for more expressive graph neural networks. Let me explain a little bit more about it. So I would like to talk about what I call the subgraph GNN wave. That is advances in more powerful graph neural networks in the last year. Basically, it's what we observed. Basically, we observed a surge in a series of approaches sharing common themes. That is the use of subgraphs, all concurrent to each other, and we somehow gathered them and to discuss them together as subgraph GNNs. And so we're gonna briefly talk about some of these approaches at the beginning, and then in the second part of the talk, I'm gonna focus on a more specific approach, that is equivariance graph aggregation networks. This is a framework that seems like to unify the other subgraph GNNs that has been proposed in the past year, and it's a concurrent work I co-authored last year with other amazing collaborators. So the second part of the talk will go more in detail about this framework. Okay, so let's start with some background and motivation. I guess at this point of the geometric deep learning course, probably you're very familiar with this. So probably, yeah, I guess we can go a little bit quick on this. But essentially, we know what a GNN is, right? So a GNN is or a graph neural network is a parameterized function on graphs whose parameters we would like to learn from data, right? And probably the most common family of graph neural networks is that is called message passing neural network family. That is all those GNNs which update node representations iteratively by exchanging messages with the neighbors. We can keep repeating message passing for a certain number of layers until in the end we can perform a readout operation to obtain a representation for the overall graph, input graph. And a very strong property and very actually advantageous property of message passing neural networks is that, as they were defined in the original formulation, they are permutation equivariant or invariant if you consider the final graph representation. This is a very important inductive bias in general that we would like to retain, right? But what's the matter with MPNNs or message passing neural networks? So the matter, as you may have probably seen during these weeks, is that no matter how we design the message and update functions, still they are bounded in expressive power. That is, they are not universal models. So there are some functions defined on graphs which cannot provably learn with message passing neural networks. And this has been characterized in terms of not being able to distinguish non-isomorphic graphs, some non-isomorphic graphs, and in particular, a series of very interesting papers have shown that essentially the upper bound on the expressive power of MPNNs is that of the 1WL test, which is polynomially fast heuristic that has been designed in the graph theory community in the past century to distinguish non-isomorphic graphs. And the way it works is basically it iterates color refinement steps, very similarly to what we do in message passing. So initially, if we say that we would like to distinguish two possibly non-isomorphic graphs, we assign the same color to every node, and then we keep updating node colors by injectively hashing together the current node color for a certain node, along with the multiset of colors from neighbors. And we keep doing this, and at each time, at every step, at every round, as this is called, we can gather the colors of nodes into histograms, and we can compare histograms to between different graphs. And as soon as the histograms diverge, then we can say that the two graphs are non-isomorphic. So the problem with this approach is that there are some non-isomorphic graphs which instead are not distinguished. So they will always be mapped to the same histogram. And so, for example, this is an infamous pair of molecules that, so there are two distinct molecules. They're real-world molecules. They are called decalen and bicyclopentyl. Of course, as you can see, they have a different molecular structure and a different associated graph. but indeed, what happens is that they cannot be distinguished by the WL test. So they will be assigned the same histogram, and therefore they will be represented in the same way. And the related limitations of this test is that it cannot count non-trivial patterns, such as, for example, the number of triangles or cycles in a graph cannot really be computed by this approach. And so, for example, in this case, the approach is not able to tell, well, in the first molecule, we have two 6 rings, for example. All these limitations, which have real practical implications, they are inherited directly by MPNNs because of what it has been shown that basically this combinatorial algorithm upper bounds the expressive power of MPNNs. So this is to somehow recap why it is important to study the expressive power of our approaches of GNNs in particular. And in the past years, there's been a lot of effort in trying to design graph neural networks which go beyond the expressive power of this combinatorial algorithm. Is there any question? No? Okay.
There is no question.
Okay. I could use some noise, but yeah, feel free to interrupt me at any time. It's going on. So going on basically, yeah, I was saying in the past years, there's been a lot of effort in trying to design novel architectures that are probably more expressive than 1WL. And essentially, the first approaches try to mimic either the generalization of this combinatorial algorithm, which are called KWL tests. They are strictly more powerful than the standard WL algorithm. But the problem is that essentially the GNNs that are inspired by these algorithms, they are non-local. So they lose this locality inductive bias, which is also a very interesting and important inductive bias in message passing neural networks. And at the same time, they easily get computationally intractable for k, this parameter k, greater or equal than 3, which is actually what we need to get more expressive GNNs. So this is not really a feasible approach, especially in practice. At the other end of the spectrum, there are approaches where instead try to get inspiration from algorithms for distributed computing, whereas the idea, whereby the idea is that we can still use a standard message passing neural network, but we can provide it with a way to identify uniquely nodes in the graph. So the idea is that these models can even be made universal if we allow them to uniquely identify centers of these messages during the message passing step. And the way you would do this is typically, in order to get unique identifiers, you use random node features sampled at any inference step. The problem with this approach is that because of this inherent randomness, it's not equivalent to permutation and the permutations. And this empirically it has been shown that it really hinders generalization. So it really creates problems in trying to generalize to test graphs and scene graphs. Maybe a middle ground could be the following. So there are these works which try to basically consider substructures in the graphs, especially those substructures which are not basically to which the standard message passing neural networks are blind to, and they either do message passing directly on top of them, or they consider the presence of these substructures to modulate message passing between nodes. Let me start with maybe this particular approach, graph substructure networks. Which I believe can be considered as a precursor to this wave of subgraph GNNs we're going to talk about in a second. So the idea is, instead of considering random node features as node identifiers, what I can do is I can choose a bank of substructures, for example, triangles, cycles, rings, cliques, and then I can mesh them on top of the input graph. And for each node, I can say, well, this node belongs to, for example, 1 triangle, 5 cycle, and maybe 2 4 cliques, for example. So all these statistics can be gathered together to form somehow what we can consider as positional encodings, structural encodings, or in a way, identifiers. They are not unique identifiers, of course, but they are still able to break local symmetries that would lead basically standard WL test or message passing neural networks to failure. Because basically each node is able to modulate the messages coming from neighbors depending on some features, structural features that standard MPNNs would not be able to capture. And because of this reason, this approach is actually strictly more powerful than 1WL for a certain choice of substructures. And other pros are that basically in this way we inject a very powerful bias into the network, which can be linked to the domain knowledge we have at hand. So for example, if you're working with molecules, we are doing molecular modeling, we know that rings are very important. And so the fact that we count rings and we know how many rings a node belong to, this becomes a very useful feature to have. It retains permutation equivariance, which is very good. And it has low message passing complexity. It's the same complexity as standard message passing neural networks. The problem with this is that counting the substructures in the first place might be computationally intractable in some cases. And of course, it's not really clear how to design the substructure bank. So which substructure to actually match on top of the input graphs. This may depend on domain knowledge, but sometimes we don't really have this, right? So this is somehow problematic to some extent. But still, nonetheless, I believe this is a kind of, can be considered as a kind of precursor to this wave of approaches which emerged in the last year concurrently. And we're going to talk about this now. The common theme is the use subgraphs, and we will see in a second how. And I've listed here some of them: dropout GNNs, reconstruction GNNs, GNNs kernel. We also have the framework I was talking about, is equivalent subgraph aggregation networks, or ESNs. There are many others. You can find them in Michael's Towards Data Science blog posts we co-authored along with some of the authors of these papers. And yeah, here I put the link. I can share the slides afterwards so you can take a look. So let's start to take a look at these approaches. Let's start from dropout GNN. Okay, so what's the key concept? So the concept is that subgraphs, well, substructures we know are important, but they might be it might be computationally expensive to match them, and it's not really clear how to, as I was saying, how to choose them, right? But still, what we can do is we can actually find important subgraphs very cheaply by subtraction. So what I mean is we may have two graphs which are not distinguishable by the standard WL algorithm, or let's say message passing neural networks, but they may contain subgraphs which are easily separated by these algorithms. And the way we can expose these subgraphs is simply by dropping some nodes very cheaply, so in a kind of almost blind fashion, right? So what they propose in this paper is you can drop each node independently with a certain probability. You run a message passing neural network on the resulting graph, which is basically, it's in itself a subgraph of the original graph. We repeat this approach for a certain number of times, and then we aggregate the embeddings that we got. And this seems to be a very naive approach, but indeed, what happens is that every node sees a slightly different neighbor each time, and this resolves the ambiguities, this local symmetries that lead basically WL to failure. And the authors show that this is enough to with some bounds to get an expressive power which is greater than standard message passing neural networks. I'm gonna just present the main ideas, and then but we can try to formalize this all intuitions better later when we talk about the ESN framework. So let me directly go to reconstruction neural nets just to give the big picture. So it's a very similar approach. The idea is that we can build on top of a famous, a popular conjecture in the graph theory community that states that it is possible to recover a graph, so reconstruct a graph from the collection of not deleted subgraphs, of all not deleted subgraphs. So the idea is you take a graph, you delete one node at a time and all the connectivity involving that node. Each of these subgraphs you get, they are called cards. You can gather all the cards in a bag or in what they call a deck, And if you consider that the deck, and you can reconstruct the original graph just looking at the cards in the deck. So the authors would basically propose something like this. So,
sorry, Fabrizio.
yes.
Yeah, there is a question.
Sure.
Yes, in the Zoom chat.
The Zoom chat, let me take a look. Slide 11, how do you choose R? Is it an hyperparameter? Yes, yes. Of course, it has also an impact on the performance, and the other, but not just on the performance, also on the properties of the algorithm itself. You can see it's if R is not so if R is actually the large enough, you might be guaranteed to sample basically all possible not deleted subgraphs. So you delete, for example, one at a time. So being it, let's say, a stochastic process, the authors actually show that you can obtain bounds on, for example, the expressive power of this approach based on this hyperparameter. But in practice, yes, you would choose them. In fact, the authors suggest that you don't really need a very large R in practice, because most of the time, basically, the times it is sufficient to drop a few nodes to already expose important subgraphs. But yes, in principle, it's an hyperparameter. Does this answer the question, or? Okay, let me continue, but yeah, feel free to keep interrupting me if there's anything else you want to talk about. Okay, so let's get back to the reconstruction neural networks. So the idea is I can take a graph, generate all the collection of not-deleted subgraphs, encode each of these subgraphs independently, and then aggregate the encodings in a permutation invariant fashion. If I do this, given that I have all possible subgraphs and I aggregate the encodings in a permutation invariant fashion, then I have an overall architecture which is actually in permutation invariant. And if the reconstruction conjecture holds, this approach is actually universal, right? So you may think, well, but is this really the case that we build on top of a conjecture? Well, the conjecture has been proved for all graphs with a number of nodes up to I think 10 or 11, and it has been proved to actually hold for families of special families of graphs. And what I mean is there is some shared feeling that it might hold. But other than this, the authors in the paper show that actually you can really extract interesting features by this process of node removal. There's actually a caveat in this. That is, point 2 in the recipe says encode each of these subgraphs independently, right? But what you would need to do is to encode each subgraphs in a unique way, right? But encoding a subgraph is as hard as encoding a graph, right? Because a subgraph is a graph itself. So the only way to, but the problem is actually that we don't really have a universal encoder for graphs. This is the problem we're trying to solve today. So what you can do is you can keep doing this recursively until you get basically subgraphs which are very small, and you can enumerate the atomic types. And in that case, yes, you may be universal. But the problem with this, if the reconstruction conjecture holds, of course, but the problem with this approach is that the computational complexity will get exponential, right? So what the authors propose is, well, you know what? I can actually use an MPNN as a card encoder, so to encode the subgraphs. So the resulting model only approximates the conjecture regime because, as we said already, MPNNs are not universal, right? But yet, even if this seems a naive approach, yet this can be provably expressive. And the expressive power of this approach depends on K, that is, on the number of nodes we retain after the perturbation. So, for example, the authors prove that if K is n-1, so if we delete one node at a time, we can actually distinguish graphs as the circular skip link graphs. I have a pair here in the slide, which cannot be distinguished by standard MPNNs. And so these make, along with other properties, this make this approach strictly more powerful than MPNNs. And for k equal to n-2, so if we delete 2 nodes at a time, we can even distinguish graphs which are not distinguished by 3WL, which is an even stronger generalization of WL. So you start to see like that MPNNs, they can somehow be used as subroutines to approximate some subgraph isomorphism, but we'll get to this in a second. I want to first show you another approach, which is slightly different than this. It's called GNN as kernel. Okay, so the authors, the motivation is, according to the authors, is, well, the bottleneck of standard WL color refinement is that this approach works by hashing, in a sense, hashing stars, right? So because we take the color of a certain node and the colors of the neighboring nodes, but in so doing, we completely ignore the the local connectivity, between, for example, between the neighbors. And according to the others, this is the fundamental bottleneck that leads WL to its failures, right? So what they propose is to shift from encoding stars to encoding actually egonets or ego subgraphs. That is basically the complete graph induced by the neighbors of a certain node up to a certain depth. For example, we can consider what the first hop, or like one hop neighborhood or two hop neighborhoods, and so on. Again, here we have a parameter k, which is actually considered to be an average parameter. That is the depth of these subgraphs, right? But okay, what do we do with these subgraphs, with these egonets? So the idea is that we can propose a variant of the standard WL algorithm whereby we change the update rule, right? So instead of hashing, as I was saying, the color of the current color of a node and the colors of the neighbors, we hash directly the all subgraph around a certain node. Okay, the problem with this, similarly as what we observed before with cards and X, right? So the problem is that an injective hash of a subgraph is indeed as hard as injectively hashing a graph, that is, as encoding a graph universally. So again, we can approximate this encoding by running an internal inner nested WL procedure only on the local subgraph. So to recap, basically, this subgraph 1WL star variant is an approximation of this more powerful subgraph 1WL approach, whereby instead of computing an injective hash of an egonet, which is very hard, we run an internal nested WL approach only to encode the subgraph, and we use the output from this internal WL approach to actually update the color of a node. In this case, the red node in the picture. And again, what we can do is we can design a neural counterpart of this subgraph 1WL star algorithm, whereby instead of running WL, we actually run an internal nested GNN. So how does this work? So instead of doing standard message passing, we update the representation of a node by running a nested GNN on its egonet. What I mean is, internally we perform message passing between the nodes in the egonet. We compute and read out. We get the representation of the egonet, and we use this representation of the egonet exactly to update the representation of the root node, of the root of the egonet. And we can keep doing this for many layers. And you can see already that there is an interesting there's something interesting popping up now. That is, we can parameterize this GNN differently, right? So for example, one thing we can do is we can parameterize it with a message passing neural network. So as I was saying, we do message passing internally in a nested fashion. And this can be made as powerful as subgraph 1WL star, which the authors show it's strictly more powerful than 1WL. So we get actually more expressive power than standard message passing neural networks by simply running this nested message passing on top of egonets. But what we can do is we can actually use even more powerful, although more expensive, of course, encoders, such as PPGN from Maron and encoders, which has been shown to be as powerful as 3WL. And if you do this, if you use PPGN as an encoder for these egonets, you can actually distinguish graphs which are not distinguished by 3WL. So again, we have the same infamous example here, these two strongly regular graphs. If you consider the red, the egonet around these red nodes, this egonets can be distinguished by a PPGN. So it means that these two graphs can be distinguished by PPGN as kernel, as they call it, this overall bi-level, if you wish, approach. Let's wrap up a little bit. So what we have? So we have that there are some common themes emerging. We have these approaches with little to no pre-engineering, in a sense that we don't really need to basically select the subgraphs to match on top of a certain graph. We can let important subgraphs directly emerge by perturbing the original graph, but in a way that doesn't really require any particular end engineer. Okay, what else? We still stay within the remit of message passing in the sense that we don't really abandon message passing completely. In the past, it's been conjectured that in order to really break this bottleneck of expressive power, one should somehow abandon message passing completely for different approaches. But what we are seeing here is that we are not abandoning message passing. We use message passing, and this has advantages, as we know. So message passing is local. It is scalable in terms of computation, and it's very easy to implement. But how is this used? It's used as a sort of subroutine, as we saw, right? So it's often used to somehow approximate subgraph encoding, subgraph isomorphism, if you wish. And this approach, which to some extent might seem a little bit naive, is already enough to gain expressive power nonetheless. Let's jump now into another approach, covariant subgraph aggregation networks, more into detail. Okay, so this is a work I co-authored with Fabrizio Bevilacqua directly, Bala, Srinivasan, Chen Kai, Gopinath, Balamurugan, a lot of students, Michael Bronstein and Agai Maron. So it's a concurrent work we published last year. And more than a model, it's an overall framework. We can consider it as an overall framework. And I'll explain you why in a second. It provides additional characterization through the lens of equivariance. And I think because of this reason, it might be interesting to take a look at this during this course. And it unifies and generalizes many other methods, for example, the methods we have seen so far. I was saying that there were many students in this project because this project actually sparked from a summer school. It's London Geometry Machine Learning Summer School in 2021, basically last year, which I invite you to take a look at and possibly apply for next year. It's a great summer school. Okay, so let's recap. So what do we want? We want some model, so a GNN, which is probably expressive, at least more expressive than standard 1WL or standard MPNNs. We would like to reduce engineering as much as possible to keep the computational complexity somehow tractable. So we don't want to get to, the very high intractable computational complexity of higher order GNNs. But at the same time, we want to retain equivariance because this is a very strong inductive bias when we work with graphs, right? And we recap that the main intuition, that is the intuition shared by many others, many other subgraph GNNs, is that even if two graphs are not distinguishable to MPNNs, they may contain subgraphs which are instead easily separated. So what I mean is, for example, if we take this pair of graphs here, these two graphs are not distinguished by an MPNN, but if we simply remove one edge, then we can run an MPNN on the obtained subgraphs, and they somehow, all of a sudden, they become easily separated. They can be easily separated by an MPNN, right? So we would like to kind of formalize this intuition somehow. So the way we can do it is we can somehow design a recipe. That is, we take a graph, we map this graph into a set of subgraphs, that is a bag of subgraphs, with a certain function, which we call a selection policy, which decides how to extract subgraphs from an original graph. And then we would like to process this bag in a principled way, that is, in a way to respect the inherent symmetries of this object. So possible policies are, for example, node deletion, edge deletion, so we remove edges one at a time instead of nodes, or we can extract egonets as in GNNs kernel, right? But let's get to the probably more interesting part, like what does it mean to keep this equivariant? So what are the symmetries of this object? Okay, so if you consider a bag of subgraphs, we have actually two symmetries which are related to one another by a direct product. And let me explain why. So each subgraph in the bag, of course, is a graph itself, right? So we would like to be equivariant to node permutation. So if we permute the order of the nodes in the subgraphs, we want the output of the network to basically have an equivariant response, right? So far so good. I mean, we are used to this, but now we have a new access, right? So we have also that we have different subgraphs in a bag. The bag is fundamentally a set. So the order of the subgraphs in the bag is not really important, right? So we would like equivariance also to permutations of the subgraphs in the bag. So as you can see, we have two permutation groups now. It's not just simply one single permutation groups that is like permutation with respect to the order of nodes. Now we also have permutations with respect to the order of subgraphs. And these two permutations actually are related to each other in a direct product. And this is because there's something which we can really leverage on. That is, all the subgraphs come from the same graph, right? So it is possible to align nodes between the subgraphs in a way that a certain node I in each subgraph can be traced back to node I in the original graph. So this means that when we permute the nodes of a subgraph, we are allowed actually to permute the nodes of all the other subgraphs in the same manner. So this means that the internal permutation, so the permutation on the nodes of each subgraph, is the same across the bag. And this is a very important intuition, and I'll explain why in the next slides. But first of all, we have this direct product between these two permutations groups, right? So how do we design a layer which is equivariant to this? So fortunately, there is a work that has been published in 2020, which study exactly the case where you would like to design a layer equivariant to a direct product between between two symmetry groups, where the outer symmetry is actually a permutation. So exactly as in our case, the internal symmetry. So maybe let's recap. So in our case, we have two symmetries, right? So an external one, which is we permute the subgraphs in the bag, and we have an internal one, that is we permute nodes in the subgraphs, right? So this work actually dealt with the case where we have an external permutation symmetry, as in our case, and an internal symmetry, which can be any actually. In our case, this is another permutation, but it's our specific use case. So other use cases, for example, for this general approach could be you have a set of images and you would like to process the set of images in an equivariant way. So in that case, the internal symmetry would be translation, right? But anyway, let's get to the juice. How can we design this layer in a way to be maximally expressive and equivariant to this symmetry group? So you need two blocks. You need L1 and L2. You need a first block, which L1, which is a Siamese component equivariant to the internal symmetry. So in the case of images, this would be, for example, a convolutional layer. And this is applied with the same ways to all elements in the set. So for example, to all images in parallel. And then you have a second block, L2, which is still equivariant to the internal symmetry. So it's still, for example, in the case of images, it's still a convolutional layer, but it has non-shared weights. So it's a different set of weights with respect to the first block. And this block is applied to the summation, the aggregation of the input elements. So in this case, the summation of the input images. And you take the outputs from these two blocks, and then you sum them together. And this will correspond to the output of the layer. So again, we have a Siamese component, this here in blue, and an information sharing component, if you wish, with a different set of parameters, which acts on the summation, the aggregation of the inputs. And we can do the same. So in our case, we won't have convolutional layers, of course, but what we're going to have is we need a block, a layer, which is equivariant, not to translation, but to permutations, because we are dealing with subgraphs, and the internal symmetry is a permutation symmetry, right? So we have something very similar with the difference being that these internal blocks, which here we have orange and yellow, ENC1 and ENC2, or if you wish, mu1, mu2, they are message passing neural networks, or in general GNNs, which we know to be equivalent to permutations. So we have basically that we instantiate two GNNs. One is shared and is applied in a Siamese fashion to each subgraph, to each of the subgraphs in the back. And we have another MPNN or GNN, which is applied to the summation of the subgraphs, where summation means that we aggregate the node features for each of the subgraphs along with the connectivity. So this, so in a way that basically we get the output from these two blocks, from these two distinct MPNNs, and we sum them. And this will be the new representation for each node in each subgraph. Okay, now we can also do something, that is, we can completely disable the second part, mu2, that is this information sharing component. What we obtain with this is an architecture which we call the SGNN. Also, by the way, the first architecture we call it DSS-GNN, where DSS stands for deep sets of symmetric elements. That is the approach we build on top of. But so what happens if we instead neglect the second component, the information sharing component? So what we get is an approach where we simply run the same message passing neural network on each of the subgraphs independently, completely independently, without information sharing. This is something like to some extent reasonable to do, right? It's feasible, but it turns out that this layer is not equivalent to the direct product of the two permutation groups, is actually equivalent to another symmetry group, which is a superset of the direct product group that we wanted to actually model, right? So if you remember, I talked about node alignment, and this is essentially what is not preserved by the read product, by this new larger symmetry group. So in the second approach. So what I mean is that in the second architecture, the nodes of a subgraphs can be permuted independently with respect to the nodes in the other subgraphs. And this layer, which does not have this information sharing block, will be equivalent to this permutation group, which is larger. And in a way to be equivalent to this larger permutation group, the model would be more constrained. So we would expect it to be less expressive. And we'll comment on this later. Is there any questions so far? It's a little bit, it's a lot, I know, but yeah, feel free to ask if you have any question on this. So far so good. Shall we continue?
Yes.
Okay, let's go. So, oh yeah, so the slide is to say that this approach, as you can see, is very general. So we have this concept of policy that generates graphs. We have this concept of processing this in an equivalent fashion and possibly also sharing information. What we observed is that many of these approaches, for example, the one we discussed before, can be captured by this framework, which, by the way, we call it equivalent subgraph aggregation networks. And so, in a sense, this framework paves the way to a unification and generalization of subgraph GNNs with bags of subgraphs, and this through the lens of equivariance, which I find it to be very interesting. But one of the first, starting point for us was the issue with expressive power. So, what's the expressive power of this architecture we designed? So in order to study that, to characterize this, we took a little detour and we designed a combinatorial algorithm that is a variant of the standard WL algorithm that works actually on subgraphs and on bags of subgraphs. The idea so is the following: we want to apply color refinement on each subgraph in the bag. But we don't do this independently. Again, we share information as we know we could do because of this node alignment concept. So the idea is that we assign a color to each node in each subgraph, and we keep refining these colors by this color refinement step. If you take a look, it's essentially similar to the standard color refinement step in WL, but we have two additional inputs, this purple and green inputs here. So we don't really have just the color of the current color of the node we are updating. We also have, as we used to have, the multiset of colors of neighbors, where now the neighbors are the neighbors according to a specific subgraph, S in this case. And then we have these two additional inputs. So the purple one, CV, is what we call the needle color. That is, we collect the color for the same node, but across different subgraphs in the back. And again, this is possible exactly because we have this concept of node alignment. And then the fourth, the last input, is what we call MV, this in green, is actually the multiset of this needle color, or we call it needle color, basically these purple ones, but for the neighbors of the node V. And basically, what happens is that we managed to prove that there exist policies such that this approach, which we call DSS-WL, is structurally more powerful than 1WL. And maybe I can also mention, so you can, what you can do is you can also disable these two new inputs. And in this case, the procedure boils down to performing standard WL on each subgraph, but independently, right? And this, we call it the SWL. And even the SWL for certain policies can be shown to be strictly more powerful than 1WL. And amongst these policies are those the most common policies which we discussed before. So, for example, node deletion, edge deletion, and egonets. Now, okay, but what about the architecture? So we proved that our architecture, DS and DSS GNN, can implement this combinatorial variant, this DS and DSS WL algorithms. So this means as a corollary that there exist policies, for example, node deletion, edge deletion, egonets, such that DS and DSS GNN are strictly more powerful than MPNNs, which is what we wanted to show at the very beginning, right? But designing this variant has allowed us to more easily compare it with standard WL, and that's why we did it in the first place. But this may also be of independent interest for combinatorial algorithms and isomorphism tests. So what about the DS versus DS GNN? So we were saying that we would expect the DSS GNN to be more expressive than the SGNN, right? Yeah, so we found some policies such that exactly this concept of node alignment allows to reconstruct the original graph, whereas the SGNN not having alignment between nodes only sees, for example, number of edges and is not able to reconstruct the original graph. So for certain policies, we showed that it is actually the case, that the SGNN is more powerful than the SGNN. And in practice, in experiments, we observed that the SGNN tends to outperform the SGNN in practice. And it's the SSGNN is better than the base encoder 91% of the time. The base encoder is the GNN we use as, if you remember, this equivariant internal blocks. So most of the time, the SSGNN is better than a standard GNN in practice. And the SGNN is better than a base encoder 75% of the time. So it's still better, just it's more likely that with DSS, with this information sharing component in addition, we get better results. So another interesting point is that the policy matters. So the choice of the policy may have an impact on the expressive power. So what we managed to show is that on the family of strongly regular graphs, which are these very highly symmetric regular graphs and very hard cases for graph isomorphism, if we use node deletion or depth and egonets, you're not able to distinguish these graphs. So we have the same discriminative power as 3WL. But if we use, for example, edge deletion, then we suddenly we're able to distinguish these graphs. And so it seems like edge deletion is stronger, as a stronger policy on at least on this family of graphs, for example. In practice, we didn't really observe a strong correlation between the performance of a policy and the application domain, but the egonet policies seem to work very well in practice, like at least consistently across settings and different data sets. Here we have an example on molecular modeling. So the zinc benchmark is about trying to predict constraint solubility for molecules modeled as graphs. And for example, we observed that as soon as we transition from edge deletion, not deletion to GNNs, the performance increase in a sense that we have a lower mean absolute error on the test set. And as you can already see, the SSGNN seem to work much better than the SGNN, especially when we use the GNN policy. In general, so we on this suite of small data sets, we observed this approach to achieve good results with compared to state-of-the-art approaches. And as we were already anticipating, it generally improves on the accuracy of the Bayesian or the accuracy of the Bayesian encoder. These are other results on other molecular modeling benchmarks from the OGP suite. I think it's interesting to take a look again at zinc, but compared to other approaches. So if we compare the results we got with our framework, we are the best performing model amongst all probably expressive domain agnostic GNNs, as you can see, and sometimes by a fair margin. At the same time, we are very competitive and sometimes even better than GNNs, which directly employ specific information. So, for example, which include explicitly the information about the presence of rings in molecules. And this was also one of the desiderata we have at the beginning, right? So we want a model to be expressive, but not necessarily to really need to inject domain knowledge into the architecture. Right, so let's wrap up. We have taken a look to this family of this wave of new provably expressive GNNs, which we call subgraph GNNs. The common theme is that they leverage subgraphs to uplift the expressive power, but still staying within the realms of message passing that is often used as a subroutine, right? We introduced ESANT, that is this framework that seems to unify concurrent works, and this is done by studying the emerging symmetry. So the symmetry is characterizing these objects as bags of subgraphs. The advantage of this approach is that well, or in general of subgraph GNNs, the advantages are that they are provably expressive. They are natively equivariant, and you really need little pre-engineering. You don't really need to be a domain expert to design the architecture. Sorry. In terms of future directions, I guess it would be interesting to study other policies, or what's a little bit more what's the impact of the policy on the expressive power and on the performance in general. Other things would be to study structured bags. So at the moment, bags have been considered to be sets, but we can also induce some particular, like some more structure on it. For example, we can consider them as graphs if we come up with an interesting notion of connectivity between subgraphs, for example. And then, I think there's work to do in studying stochastic policies, that is policies which subsample subgraphs. Because there is this, we have this intuition that we can still retain some approximate form of equivariance, and this is still very interesting because this would allow us to reduce the computational complexity, but still retain some form of approximate equivariance, so still this strong inductive bias on graphs. And with this, I conclude the presentation, and I'm happy to take any questions. Yeah, thank you very much.
Yes, thank you, Fabrizio. So there's a question in the chat.
Yes, the SSWL and such methods are evaluated. Okay, so the SSWL, we didn't really implement it in practice in the sense that it was so it is a combinatorial algorithm we used on the theoretical side to then study the expressiveness of the neural counterpart. And then we, of course, implemented the neural counterpart, and that is the SSGNN and the SGNN, and we applied it on a series of benchmarks. In particular, we focused on molecular modeling. So the idea is you model a molecule as a graph, and then you apply our method. So what does it mean to apply our method on a molecule defined as a graph? It means that we take the graph corresponding to the molecule, and again, as I was explaining, we apply policy, so we extract subgraphs, and we process these subgraphs in an equivariant way. And then in the end, basically, you have a representation for each subgraph. You aggregate these representations again well, in this case, in the end, in an invariant fashion, and then you would like to give this representation to a classifier to predict, for example, molecular properties such as toxicity and so on. So there are other results on synthetic benchmarks. I haven't showed them to you, but yeah, we also evaluated this approach in terms of, like, purely in terms of its expressive power. So there are synthetic benchmarks where people try to run GNNs in an effort to disambiguate graphs, which we already know they are not distinguishable by standard message passing neural networks. So, for example, there are the data sets of circular skip-link graphs, and yeah, we actually indeed evaluated the SGNN on these benchmarks, and in most of the cases we got perfect accuracy, mostly because this basically showed that the approach is indeed more expressive than standard message passing neural networks, which they have random guess accuracy on these benchmarks, but still these graphs were usually like 3WL distinguishable. So yeah, this explains also why we really managed to get up to 100%. So we did this kind of evaluation, if this is what you were asking about the expressive power. Yes. So if we were to go back to the start policy when using the ESON framework, do we go back to WL networks? Oh, okay, very interesting. So instead of considering GNNs, you consider stars, basically. Let me think about it. So if you don't do anything particular, yes, I guess you would get back to the standard WL. Yeah, if it's, for example, just one. It depends also on, so if you take, for example, PS, WL, and you extract stars, so if stars are just one-off stars for each, and each subgraph is a one-off star, and you don't have any information sharing, actually what happens is that it might even be less expressive than WL, because you are not able to basically propagate information from further nodes. So the algorithm would converge very quickly. So if the star is shallow, it may also potentially lose expressive power in this case. If you have a form of information sharing, for example, this needle coloring, maybe you can make do with that, and maybe you can get to standard WL. But yes, this, as you can see, some policies are very trivial and are actually not useful or detrimental. For example, another one is simply take edges. You have, like, each subgraph is an edge, right? So this is also a very non-useful policy. Yes. But yeah, a very interesting question. So we have some intuition on how to choose the policies in the future. Yeah, good question. So as I was saying, we don't really want to have pre-engineering, but there's still some pre-engineering in the sense that, like, how do you choose the policy, right? So in general, as we were saying, the ego policy works very well. Typically, similar, like comparable, or is comparable to node deletion, or even better. This is an active also area, I think. Well, not, don't see papers exactly on designing policies, but there are new policies emerging in recent papers. For example, there are new papers where people try to use node marking instead of node deletion, and they show that this basically substitute node deletion. So the idea is you don't necessarily need to delete a node. You can mark it with a special feature, and the fact that you mark this with a special feature actually um, allows you to still break symmetries, but without actually altering the connectivity. And the idea is you can simulate what would happen with node deletion anyway. Another thing is, I think we have also a better understanding of what it means to choose a policy, like what's the impact of the policy. So there's some more recent work I did. For example, we realized you can also gather policies in classes. For example, you have policies which are intrinsically not based, right? So if you think of GNNs or node marking or node deletion, you can always find a bijection between a node into an original graph and a subgraph you generate. So this actually gives you more structure, and you can consider them in a class and study what the characteristic of this class of policies. And we actually did it, and we found out that if you have this kind of policies, you always have an upper bound in expressive power if you use a standard MPNN encoder, which is 3WL. So the upshot is that if you want to go beyond 3WL with an MPNN based encoder, you need a policy which is not node based. For example, something like edge based, so you mark 2 nodes at a time, you delete 1 edge at a time. So yeah, there's at least some recent work which tries to characterize these policies into, like, for example, classify them into classes and study the features of these classes, these families of policies, and their limitations. So yeah, for sure, there's some work with this. In general, if you have domain knowledge, it's always good to take that into account if you want to design a new policy. But yeah, this is what I can probably answer at the moment. Thank you for the question. Very great. Yeah, they were really great questions. If there's nothing else, yeah, I can also mention, maybe related to this question, let me top up on this. I forgot to say there are also works, very recent works, which try to learn the policy directly. So instead of designing the policy, what you could do is you can learn it end to end. For example, with some particular approach to backpropagate through the discrete structures. Well, you could do it, for example, with reinforcement learning. So the problem is essentially that the selection of edges, these are discrete operations, and it's not really obvious how to backpropagate through this, through the policy itself. But you can, for example, make do with reinforcement learning, or something which seems to be also very effective, that is to use approaches like based on perturbations for like implicit differentiation and propagation through discrete structures. So there are these works which basically propagate through the combinatorial algorithms, and they have been tried. There's been an attempt to use these approaches to learn policies itself, like the policy itself from data directly, while like in an end-to-end fashion. if you're interested in this, so there is like this approach that's called implicit maximum likelihood estimation, AMMI, which tries to do this kind of things. So the idea is, for example, you want to backpropagate through, say, an integer linear programming problem, for example, like or something like, I don't know, Dijkstra for shortest path. The idea is you can do this with some tricks and based on perturbations, and yeah, you can then basically learn the parameters of this mixed models and to end. Yeah, so there's some work on this as well. I'm not an expert in this kind of approaches, but yeah, for sure, there's movement on that side as well.